Science 10. Last topic for Chapter 5 is on potential energy. And remember that kinetic energy was the energy of motion. So we had to use mass and velocity in that. So it was kinetic energy was half mv squared. For potential energy, that is just the potential to actually do some work or move. So if you were thinking of moving up a hill with your bike or biking down the hill, you are showing kinetic energy. There's a mass, there's a velocity. If you are at the top of the hill though, and just standing still, you have the potential to go down, potential to do work. So this calculation for potential energy is going to be mass times gravity, which is, by the way, 9.81 meters per second squared, so the acceleration due to gravity, times the height that you are above the ground. So this will be the one formula that we are working with in today's lesson. Pretty easy. You will see as we go that there is potential to do something, giving it potential energy, and in a crossbow, when you are pulling it back, there's kinetic energy of motion. Holding on before you shoot, that's potential. The idea of having potential energy stored in an object could be like stored as food or fuel, like in a battery, the chemical potential energy, or it could be because of the position that you are. So you've got a highest potential energy at position A. If you were at the very bottom, let's say, or right there, you would actually say you have zero potential. There's nowhere to go further down, okay? And with the types of potential, elastic, you can imagine pulling an elastic back as potential to do work when you let it go. Shoot a paper wad across the room or something. Potential energy in as chemical is stored in food or fuel. Nuclear potential, oh, I guess I have some descriptions of that in the following slide. This is the holding on to the pulling the arrow back. That would be potential, potential elastic energy. The potential chemical energy found in bonds of food or fuel. They can provide energy once they're digested and broken down. Nuclear potential is the stored energy in a nucleus of an atom that can be split, rearranged, and release a lot of energy that does some kind of work there. And gravitational potential energy is the one we'll work with the most here, and it's the energy stored because of that object's position or height above the ground. And we do have to, in our formula, look at the height and look at the mass of the object. Weight is how much gravity is pulling on something from grade 7. And mass is the matter in that object. So if you have, if you're doing a measurement on the moon, for example, your weight and how much gravity is pulling on you will not be the same as your weight or how much gravity is pulling on you on the Earth, whereas your mass could be the same in both places. So we're going to look at weight in newtons in our formula, and mass in kilograms, and acceleration due to gravity, which is a given of 9.81 meters per second squared. And that will be the value that is on your data sheet that you will be using for acceleration due to gravity. You'll notice that this force is equal to mass times acceleration is basically the same formula that we had seen before, and now we're just looking at mass times the acceleration due to gravity, but it's still acceleration, so it's no different than the F equals ma that we have seen once before. And so here's our formula for gravitational potential energy. It's simply mass times gravity, acceleration due to gravity, times height. And you just have to be careful that you know that the energy is in joules, the mass is in kilograms, the acceleration due to gravity is meters per second squared, and the height then will be in meters. Just so our units all jive, you have, and are actually equal to joules, you have to be careful of making sure it's kilograms for your mass and meters for your height. So the work you do to lift the object will be exactly the same as the potential energy that it has. So if you lift a book up, you're doing kinetic energy as you lift it up, but when it's up there, it's got potential, and it's got the potential to do work as it falls down. It could maybe crush something. And when we look at the fact that work is equal to force times distance from way back, the fact that force is mass times acceleration, or acceleration due to gravity, and distance would be the same as height, you can see where this formula actually comes from, and it comes from the components of other formulas you've already seen. But this is the one that we're going to be working with today. And this example with the Christmas tree, you can see that this star was 16 kilograms, multiplied, that's the mass, the gravity, 9.81 meters per second square, is for all things falling to Earth, and it's up 2 meters high. And so you multiply that, and you get your answer, 3.1 times 10 to the 2 in joules. Pretty easy to use this formula. This question, to look at it from as one example, before you guys try a few for yourself out of the questions in your notes, is looking at this diagram is in your note package, but basically this book has the potential to fall to the table, it has the potential to fall to the chair, and a potential to fall to the ground. So there's 3 different possible questions you could be asked on this one. And so the example for number 1 that we're working through together here in your questions is you always write your formula down, guys. Your potential energy here is mgh, and I should actually just put a potential here. And your mass of your book has to be in kilograms, 1.2 kilograms times 9.81 meters per second squared. And notice I use 0.7 meters because although they give you an answer or a measurement of what the distance is that it would fall, the 140 centimeters that this holds to the floor, to the shelf is, you have to subtract the 70 that it would fall to do this first question, to fall to the desk. And remember that the desk here is 70, and because this whole area is 140, this is also 70. So you're subtracting here 140 minus 70, so the answer is 70 centimeters, but you need to use the value in meters. So 70 centimeters is 0.7 meters, which is why I used 0.7 meters to calculate, and the answer is 8.2 joules. It's 1.2 times 9.81 times 0.7. It's 8.2 joules, and when it falls, it loses potential energy. It's going to be on the table now, and it'll have a less potential when it's falling towards the floor. So that is our first example that I did with you. There's a few more to do in your notes, and you can check back with the key. After that, guys, there's a review that list of questions that you can do that I will post photographs of and answer keys of.